This video contains the solution to number 4, 2000, actually not sure what year, but it will be in the title. This is a number 4. A rare example, or rarer example, of a volume area problem. Actually, yeah, that's true, just have volume in it, with no calculator. So let's see how we can do with this. Problem says, let f be the function given by f of x is equal to kx squared minus x cubed, where k is a positive constant. Let R be the region in the first quadrant bounded by the graph of f and the x-axis. I want to find all values of the constant k for which the area R is equal to 2. Alright, let's see if we can do that. So first of all, we've got the function f of x is equal to kx squared minus x cubed. Where does that cross the x-axis? Well, take a little bit of ingenuity maybe to figure that out, but maybe not that much. X squared, I'm just factoring here, k minus x. It looks like this is going to intersect the x-axis, or in other words have zeros, when x is equal to 0 and when x is equal to k. So that's the first thing we need to figure out. So now we know when we find the area, we're going from where to where. So we want the area from 0 to k, because we want the part in the first quadrant, right? So it would be from 0 to k, where zeros are. And we would like that area to be equal to 2. So we want the area under kx squared minus x cubed from 0 to k to be equal to 2. Let's see if we can do that. The antiderivative of kx squared would be kx cubed over 3, and the antiderivative of x to the third is x to the fourth over 4 from 0 to k, and we still want that to be equal to 2. So let's plug k in here. That gives me k cubed, let's see, that's k to the fourth over 3, because I already had a k there and there's 3 more of them, and then that's, when I plug k into that, that's k to the fourth, k to the fourth over 4, and when I plug 0 into both of those, it just is 0, so I need this to be equal to 2, and getting a common denominator here, a common denominator is 12, so this would be 4/12 minus 3/12, so that gives me k to the fourth over 12 equals 2. Now k to the fourth would be equal to 24, and k is equal to the fourth root of 24. And as odd an answer as that might seem, that is the correct answer. Part B. For k values greater than 0, and they told us k is a positive constant, they're reinforcing that here, write but do not evaluate an integral expression in terms of k for the volume of the solid generated when R is rotated about the x-axis. Well, we already know what the integral for that region looks like. Right, it looks like this. So if we want to rotate it around the x-axis, that's just 0 to k. Remember, when we're rotating around an x-axis or y-axis, it's basically pi r squared. Those are our disk slices. So pi, the radius, it's not hollow or anything, it's just one function right up against the x-axis. It's the radius squared dx. And that's it. That's how you find the volume of a solid revolution, and we know that it goes from 0 to k because we already figured that out in part A. Part C, for k is greater than 0, write but do not evaluate an expression in terms of k involving one or more integrals that gives the perimeter of the region R. Well, let's see what's going on here. That region R, it's a bump of a cubic that looks like this. This bump that goes from 0 to k. So if we want to find, and that's the region R, if we want to find the perimeter of that region, we need to add two pieces. We need to find the length of this curve, and we need to add that length. Well, this length right here is just k, right, from 0 to k. And this is the length of that curve. So what's the formula for that? Remember, the length of a curve is the integral of, from wherever to wherever, in this case it would be 0 to k, of 1 plus dy dx squared dx. Remember, there are three forms of this that we learned, one for parametric curves, one for polar curves, and then this one for regular old functions. So we need to find that dy dx. Our function is here, so let's see, dy dx would be 2kx minus 3x squared, and we put that in there. So let's see, our whole perimeter would be k, that's this base, plus the integral from 0 to k, the square root of 1 plus the derivative, which is 2kx minus 3x squared dx. And there's nothing more we can do than that. So that really was no calculator. We didn't have any numbers, really. I suppose we did a little bit here to find that value.